Okay, welcome everybody. So in this video, I want to state a really powerful theorem from linear algebra called the singular value decomposition. So let's let A be any m by n matrix with rank R. So this means A has R linearly independent column vectors. Then there is going to exist an m by n matrix that we denote with the Greek capital letter sigma. And just to make sure we understand the dimensions of this matrix sigma, so this letter D is representing an R by R matrix that consists of the first R singular values of this matrix A. So we've got sigma 1, sigma 2, all the way down to sigma R, and then we have zeros off of the main diagonal. So that's what's holding this position. So sigma is an M by N matrix. It has the same size as matrix A. So if over here we have an R by R matrix, this means to add up to a total number of n columns, we have a bunch of columns of zeros after this diagonal matrix. In fact, we have n minus r columns of zeros, and below this matrix D, we're going to have m minus r rows of zeros. And the entries that make up the diagonal piece of this matrix sigma are going to consist of the singular value, sigma 1, sigma 2, up to sigma r. So recall these singular values of matrix A are the square roots of the eigenvalues of A transpose A. And so we're going to arrange these singular values in descending order down the diagonal of matrix D. And then off of the diagonal, we have a bunch of zeros. So this is going to allow us to take this matrix A, which we started with an m by n matrix, and we're going to be able to decompose this into an m by m orthogonal matrix U times an m by n matrix sigma, which is not quite diagonal, and then we multiply on the right by matrix V transpose, which is going to be an n by n matrix, and the matrix V is going to be an orthogonal matrix, and we're going to multiply by the transpose of that matrix V. So we're going to be able to take A and write it as the product of an orthogonal matrix times a sort of diagonal matrix times the transpose of another orthogonal matrix, where now the matrices U and V, they're not equal to each other. They're not even the same size. U is m by n and V is n by n. So we're going to need to pay attention to these various dimensions as we do these decompositions. And so this decomposition, factoring A into the product of these three matrices, U times sigma times V of T, the transpose of V, is what's called the singular value decomposition that we often just shorthand with SVD for short, to stand for singular value decomposition. And as with the diagonalization process for square matrices, the matrices U and V, these orthogonal matrices that we identify, are not going to be uniquely determined. They're going to depend on our choice of eigenvectors that we use. However, the matrix sigma is unique up to the ordering of these diagonal entries, which we choose to do in descending order. So if I'm going to put the largest one first and then the second largest and so on, this matrix sigma is a unique matrix. The other two matrices, U and V, in this decomposition, again, are not uniquely determined. And so it's going to be difficult, I think, for you to kind of wrap your head about this process, the singular value decomposition, without doing some examples. So on the next couple of videos, we're going to work through a couple of examples to see how this process works.